Today, in honor of our majority guests from Indonesia, I wear my Indonesian batik. Brought from Indonesia by my colleague, former student now. She is colleague, Dr. Kartini. She visited us. Dr. Kartini is out of it. I visited only Bandung in 2005 on Ikram 5. So, we will talk on modules today. In the first half, we talk on modules. I'll talk on modules, examples of modules, sub-modules in the quotient modules and the isomorphism theorems. That you see all these things going on parallelly. Of course, groups, subgroups, quotient groups, homomorphism theorems. Then the same for rings and the modules. You can associate starting groups, how to generalize. This way, historically, that was such kind of generalization. Taking for the groups, then extend it to rings, then they see no need to introduce that binary operation, second binary operation on ring itself. We can take something else and joining to your abelian group, make another operation which we will call action of ring. That is that structure was appeared in that action we'll call module. Okay, so this is a definition of left module. R be a ring with identity. This is another condition. Left R module is abelian group first, means M, whose addition is a abelian group, and this mapping, this function is given function f from Rm into R. I brought my points marker because it's not enough. Okay, so I have function f from Rm into M. It is additional structure I want to define for M. It is called scalar multiplication. Then this function must satisfy these four conditions. Yesterday, 2 lectures were too fast because that was undergraduate level material. This one is a bit high, so that's why I don't want to be fast. So any question, any discussion, we are welcome. Okay, so what does it mean? This means multiplication operation is additive and with respect to action, of course. Then if you take, you see, this function must respect operation in R and the operations in R, because we have 2 operations there, and additive operation in M. So that respectability is given by these 4 axioms. You can pay attention to the first one. Here, this plus operation in R. This is in R. This plus operation in M. This is action. So R plus S acting to M must give R first act to M, and R S must act to M. And this plus operation in M. See, this is given as a plus in both all cases, but the different addition operations. Addition operation here. Let me write it first. R plus MS. This is action. M. Your function f must be according to that addition operation there. Just addition operation, I will denote as addition. So M f of Rm. Now result of your function. So this is element of in M. Sorry, here R. Here M. F Sm. This is in R. This is in M. The second one also can be easily written as given the M plus N. This is M plus N plus operation in M equals Rm plus R. So F. Rm plus F S Rm. Here is in plus in M, here also plus in M. But next one is product in R. F R product in RS acting to M gives you, first you act by S, then by M. So you have F of R, F of S, M. Here, your ring product, here action, your F. So this is number 3. Number 4 is just if you take identity of your ring, then acting to any element of your M, it must be for any M. So this for axioms, which you can see axioms different R and okay. Then next one is right R module. Now you will multiply, you will add to your abelian group from right side. This is left side. So you put here R, M, result is if you multiply X from right side, then it is called right module. Your M is called right module. Your M is called, this case, your M is called left module. Left R module, this case is called right R module. Axioms are similar, just multiplication from action from right side. Okay, now if your R is a field, then easy to see these axioms exactly axioms of vector space. So that's why R module where R is a field is a vector space. It's a vector space. So how many axioms? There will be five axioms of abelian group in the class. Here, that function is given number 6, then plus 4. So altogether 10 axioms. But that 10 axioms exactly in vector space. Vector space first axiom is the second half, you will see. First axiom is addition operation. Then sixth axiom is multiplication by scalar. Then other axioms, first series axiom related to abelian group, and then another 4 axioms, they are relations between scalar multiplication and that abelian structure on vector space. That is such an observation. Okay, then actually, if you have some result for left R module or right R module, you can convert it into another case. If you have some result for left R module, then you can convert it to right R module. But each your module must be over commutative ring. You will see later on why commutativity is important. So examples first. Let R be a commutative group in this example. Like example number 5. If R be a commutative ring and M be left R module, then M can be equipped by right R module structure. This is given M. R is Rm. So you will define another function. You have f function from f is from R and into M. So I want to consider my M abelian group as a left R module. What will do? I will define another function. Function G, which is from M R into M, which is defined as follows: G of MR is F of Rm. In both cases, result in M. Start to verify properties now. Axioms, data axioms. First axiom is I claim this is a right action. Right action. What should I do for that? I should take M R plus S. This must be MR plus MS. Maybe if you put that, then what you will get? In reality, if I write it as follows: MR R plus S equals, this must be G and R plus G MS. Let us check it. This is, according to the definition, F of R plus S M. But this is right module. I can distribute. So the result will be F of R M plus F of SM. When I will convert again, this is G of MR plus G of MS. So first action easy to verify. Let me check importance, to show importance of commutativity, axiom number 3. but we need axiom number 3. Commutative we need for axiom number 3. Okay, let me check. So G M R S equals F of R S R times S M equals F of R F of S M, which is G of because I should write M here and R there, F of SM R, which is G G M S and R. Correct? R. Yeah. Now what we'll do is it should be, if I write it normal way, that is, it should be G M S R. You see, here I have M R S. Here I have M S R. If my ring is not commutative, I cannot commute. So result G M R S. So result will be if it is commutative. That commutative is used here. Okay, so first example, if you have left module, right module, results on left module and right module can be converted to each other by using this notation. This defining in another. Example number 2. Let S be a ring with identity R be a subring of S containing the identity of S. Then S is the R module with a scalar multiplication being the multiplication in S. In particular, if F is a subfield of field K, then K is a vector space over F. You have a ring, and it is subring. Ring we can consider as our module of subring. We have S, this is R. You can act by R to S, just usual multiplication. You have R, S, result of course in S. Result of S. ring and RP subring. The result best you can just use the R module. Because if you take element of R, multiply by element of S, but this is part of S. So that's why product of two elements of S will be in S. Then all axioms, all these four axioms you can easily check. They are say result of ring axioms. Okay. Now let us consider ideal. Now I will consider another case, which is ideal in R. by definition of ideal. Multiply, if you multiply by element of R, then you will get the element of R. F of R of S or R of M is just R times M. The product in R. Product is product of R. Your function is given. In this case, your function is defined by ring product. Okay, now, of course, if you consider left ideal, you will get left module. If you right ideal, you will get right module. Right R module. Okay, so now here is, if you have ideal, which is abelian group, any ideal is abelian group with respect to addition operation, you may construct this abelian quotient group, and you can define R module structure on this abelian quotient group. How to define that function? Function R acting to this class is this class. You should define R cross R over I. The result must be R over I. Function F is defined as follows. You will take element R from here, then any class here, say S plus I, then the result is you multiply representatives. This is element of R, then plus, take that class coset, which is represented by element R times S. You can check this function is a well-defined function from this set to that set, from R cross R over I to R over I. Well-defined function. What if you take the same elements S plus I, S prime plus I, two classes, two cosets with different representatives, one of them is S, another one is prime. Then S minus S prime is element of I. Then R times S minus S prime is element of I. So result R times S plus I, R times S prime plus I, also the same. Means if S plus I equals S prime plus I, then the image also are the same. Means this well-defined that operation. Well-defined of our function. Okay? Right. Now, ring axioms now. Module axiom. Module axioms easily can be verified again. Easy. Next example is on abelian groups. On abelian groups, if I consider abelian group, I have a ring of integers as an R. You can take an action of this ring on A. What you will do? You will add few times I by itself, n times. Once you add n times A by itself, you will get action of integers on A. And A is defined n times you will add, if n is positive, minus A you will add n times. In this case you will get negative case. 0 is if your n is so thus you will get action of C on A. You will get Z A to A. This is your function. Again, you can easily check these four axioms are there. Because add a n time, then another divide n into two parts, n1, n2, and the result will be the same. Which is the first axiom. If you take n1, n2, add your a n1 times n2 times, then if you take combine, then you will get n1 plus n2 times. Which is the axiom. Axiom number 2 is the same because if you take n times a plus b, which is na plus nb, this is a okay. Then few more examples. Now let us consider this is matrices. Matrices, n by n matrices over ring R. Over ring R, they are, you can define R module structure in R. How to define R module structure? Yes. R module, M and R module in the R module. M and R, what is the difference? How about M and R module? Mn means n by n matrices. N by n matrices, quadratic matrices. Here, m rows and the n columns. Let me define that function. F function now. So you have now as an m, you have m and over your R. Let's take first as an R. I cannot denote R again. Let me denote as a A. M and R. This is the ring. Ring of n by n matrices. Then let us insert action. Here you have M cross n matrix. Here you have n cross n matrix. You multiply by n cross n matrix. Result is M cross n matrix. This is element of C here. If you take here, or A as denoted to the element of K. Okay, let me take this is the SS. So this is A from M and R. This is let us denote this B from say M and N. Then result just multiplication. I will multiply N A times B. Result is M. This is your function F. So we get right module. Verification of that axiom is here. So, matrix product. See, just number 3 maybe is tricky. Here you can take A here, multiply B and C. We have A, B, and times C. Multiply n by n matrix, you will get n matrix, you will get n matrix multiplied by A, m matrix, you will get m matrix. Here also the same. Here you will get m matrix multiply by n, you will get all the additions is checked. In particular case, you will get just rows, and you may consider these rows as an R module. This M is one piece. Then if R is a field, then you will get n-dimensional affine space over F, Fn. Here an example. Let R and S are rings. Let there be rings. Then phi is homomorphism from R to S. Then M be S module. Module with respect to this S. Then we can acute R module structure by R module structure to this our abelian group M. How to do it? I will multiply this element of this M from left side as follows. I will take image of my R in S, but with respect to S is this left module. Your function is defined as follows. F of Rm is there. G, because in S you have another function. G phi R M. This is the element of R. This is the element of M. This is the element of S. This is the element of M again. G is detection. S, M to M is given by G. Then F you define F from R cross M to M. You will define it here. Now easily check on these four axioms. The result is R module. Now this interesting case. If you take M by N matrices, you make them as an R module. Write R module as follows. You take R and include it two M by M matrices, quadratic matrices, by multiplying your identity matrix by R. In diagonal you have 1, 1, 1, 1. Then to each R you will assign to that scalar matrix. It is actually inclusion. You will get R. You take R, then you can take any dimension, any size matrices. You can include your R into that quadratic matrices. How to do it? You will take R, you will assign R, and so on, R0. This is R times identity matrix. If you take N, you will take N by N identity matrix. So again, you will include. For any M, you can do it. So that's why if you take, if you include your R in MR, then with respect, just now, we have shown if you take MMR, then you can multiply from the right side. So that's why you will get left module. If you take, if you include your R in MN, N by N matrices, then you can multiply from another side. You will get the right module. this is an example. Just now, we considered the example. What you will do, you first R include to M R that way, then multiply this from that side. So R cross M N to M. So this is the R module. Left R module. If you now R, if you include M and R, then of course you may multiply it from that side. And R and result will be M and R. So you will get right. Right R. Okay. Then another example on abelian groups, endomorphism of abelian groups. Endomorphism of abelian groups is the then you may consider your abelian group as a left module over endomorphism ring of that your abelian group A. As follows. So phi A, because phi is endomorphism from NA. Then multiplication operation you define as the image of your endomorphism. Your R operation, your F operation is defined as follows. You will take phi from this cell, A from this cell. F is phi of A. This is definitely element of A. Again, we can check this is action, left action of endomorphism ring. Okay, let me now start to talk on submodule. M be a R module, and it's a subset, and is called submodule if it is independently R module with respect to that function which is defined in M. For first structure, for abelian structure, no problem, huh? Because if you take N, it is a subgroup of N. Must be subgroup, abelian subgroup of M. But action you will take which you act R to M by function F, restricting your F to your N. Because you have here as a sub you have N, so you can define G from N, R N to N as F restricted to R cross N. If restricted F to R cross N, then you will get function from N cross N to N, and these four conditions satisfied. In that case, N is called a submodule. Here is a criterion to be for subset to be submodule. Let M be a module, R module. Non-empty set, non-empty subset N of M is submodule if and only if R, M, plus M, Rm plus Sm is element of N for any Rs from S and Mn from N. That is like groups and rings, subgroups and rings case. You see, algebra, how algebra makes your life longer, because to verify subgroup, instead of 4 axioms, we have to verify only one for non-empty. If your subset is finite, or your subgroup, your group is finite, then it is enough. No need to take a inverse also. It might simplify your life. So there, how many times? 4 times. Huh? Then in ring case, you should verify how many axioms? 5 plus another 4. Yeah, associativity, left, right distributivity, 8. So instead of 8, you will verify only 2. 4 times. 4 times 4 times, 16 times. Plus, here you have 10 axioms. Let's say 10. Huh? 10, you should verify only, okay, 2. Then 5 times again. 80 times. Oh, good, right? Algebra makes your life longer 80 times. Okay, that is easy, because first of all, you should verify for N to be an abelian subgroup, which is M is 1 and S is -1 case. M minus R, M minus N must be in R. But for all these are the cases, you should take R and S, take different values of R and the case. You can see this all can be provided by this only one condition. Okay, next now consider submodules generated by a subset of M. There is a proposition R be a ring and M be a R module, and N alpha runs some index lambda is the family of submodules of M. Then intersection of all these family of elements of this family is a submodulity. For abelian groups, it's true, right? Already yesterday we discussed it. This condition also, this function also, for each of them, multiplication products, this scalar multiplication is defined. If you take any element from here, multiply it by R, then since you will take from intersection, that element belongs to each of them. You will multiply your R by each of them. Result will be in N alpha for any alpha. Since your RS in your RM in N alpha for any alpha, then it is in intersection also. So that's why this function is defined, and all these properties are true. Then, if you consider any subset now of M, then of course you may consider submodules containing this subset X. Minimal submodule containing this X is an intersection of all submodules containing this X. It is denoted by this bracket, X in bracket. If X is finite set, then of course you have finite number elements of M, and generate your module structure by using that finite number elements. that module generated by this finite number element is called finitely generated submodule. If module itself is generated by finite number elements, then module is called finitely generated module. If your submodule generated by one single element, in that case, that submodule is called cyclic. So module itself is called cyclic if it is generated by one element. This is a, by the way, this is a description of generation by X. Like in group's case, this is such kind of finite summations. Summation multiply finite number elements of X, because you cannot take infinitely many summations. Terms of summation cannot be infinitely many, because in that case you will come across with convergency. If the summation is finite, no problem. According to the definition of abelian group, you can add finite number elements, the result will be a limit of abelian group. This is a limit of abelian group. Adding, you will get a limit of abelian group. So that's why if you take element of this form, taking difference of element to this form, you will get the element of form, because finite sum minus another finite sum. You can write taking together is a finite sum. If you take it different, if you have summation with respect to k, there are I or rk, xk minus c. Here I will take say L, S, L, Y, L, C. Of course, because here you have finite number terms, here also you have finite number. Radianality is, you can write it as a one summation, which is say with respect to t, say here, say p, t, and ct. Again, the result will be finite number summation, and this is the element of S. Belong to the summation sign, and multiplying element of this form multiplied by r, you can put here your r times rk is the element of r again, and multiplied by xk. Again, you will get the element of that form. All these properties you can easily, the axioms you can easily verify. Okay? Right, so just I have to repeat the split of homomorphisms now. You have two R modules now, M and N. Then homomorphism from one R module to another R module is function from N to N, M to N, which preserves structures of R module in R module structure in M and R module structure in N. First of all, this function must preserve additive structure. This addition in M, this addition in N. Then here R times M is R module structure here. Then here R times Fm is R module structure in N. We should try this one is by using function, this function. This must be used taking another function. Because action is given by different functions in M and in N. So that is function preserving that R module structure in M and N is called homomorphism of R modules M. if m and n are the same, then it is called R-module homomorphism. It's called R-module endomorphism. If it is invertible, then it is called isomorphism. If it is monomorphism, if it is one-to-one, this function is one-to-one, then it is called monomorphism, model monomorphism. Epimorphism, it is one-to-one. Isomorphic models are denoted M this way. This is a kernel. This is a kernel which those elements of M which send to 0 and then your function f. Here is image of M as usual function image. Those elements of N which can be represented of Fm form. That is the image, which is nothing related to model structure, right? So this is a kernel, this is an image. Kernel of F is a submodule. We will see later on when we can formulate the same kind of theorems as fundamental homomorphism theorem for rings and for groups in the rings. Now, let us consider R module M and it is submodule N. Then M over N is quotient a group, abelian group. Then let's say, let us consider here R module structure. Define R module structure. We have defined already. R times M plus N, I will define as an Rm plus N. This action function f r m plus n is initial function in m plus class represented by rn. M, it is submodule N. I will consider first quotient group, M over N. M over N. Define our module structure in M over N. So it is defined as follows. I will take F, R, acting to M plus N. This is a new function, F bar, which is F of Rm plus N. Well, this is your old friend, R module structure on N. So result, M by N is an R module. All that axioms can be easily verified. This function is well defined and all axioms can be easily verified. Then there is one ring homomorphism. Since I have R module, and this one also is R module, the M R module. And M over N also R module. There is one homomorphism between these two R modules. It's called natural homomorphism. It is denoted as pi. Pi is from M to M over N. This is well known for groups also. How to define it. Pi over of M is M bar, which is M plus N. Coset with respect to M. So this is easily verified. R model homomorphism. Since with a billion, if you consider it's a set, this projection is equimorphism. It's usual group, so that's why onto, onto, and you have homomorphism. This R model, this R model. You can verify that conditions are serving. Hello?
Question. In respect to the question module.
Question model,
Yeah, in which case, the question must be a normal subgroup.
No, here M is abelian group.
Just a subgroup only.
No, M is abelian group. No need to do it. Require that because in abelian group, any subgroup is.
In a single abelian, if you have the action of R from R as a mapping from M to M, then is it necessary that it's a group endomorphism?
Which one? M to M. You know, different R modules.
Same R module, but the action of R, element of the ring, that is acting on sending to XR. Is it necessary to be an endomorphism of that abelian group?
It's not related.
Okay, sorry.
So first homomorphism theorem, I will try. 5 minutes. Then R to a V. Then F R module homomorph from M to N. Then since channel of M is a submodule, you may form such kind quotient module. So you have to know, you have two R modules. One is this quotient module, another one image. Image also is submodule, by the way. You can easily verify image of homomorphism, module homomorphism is a submodule of second module, N. So you have two modules. One is that quotient module, R module. This is the image R module. These two R modules are isomorphic. So isomorphism can be easily defined as follows. You will see. Let me take that isomorphism. F bar. I will denote this bar, which is M plus kernel of F is F of M plus kernel of F. This isomorphism is given by this function. Image. By image, if your homomorphism is onto, then you will get this quotient module is isomorphic to N. Otherwise, just image. So you have such N isomorphic. Second isomorphism theorem, exactly the same we have for groups. For groups we have N times P over P is isomorphic to N times N intersection P. Yesterday we discussed it. The same theorem holds for modules also. The same function can be easily proven. That function is R module isomorphism function. That isomorphism between this group, that function itself will serve as a homomorphism of R modules. Isomorphism of two these two are modules. The third isomorphism theorem is the same. If you take some subgroup of n, then you can cancel n. So m over this quotient module and this quotient module are isomorphic. Easily check. Here is corresponding theorem stating following. Let me just draw. Otherwise, you're going to start to not happy without proving. So what I have, this is your n containing, this is your submodule n. Here you have m over n. If you take any such an submodule of n containing your m, then you can send it to some submodule of m over n. Submodule of m over n. Moreover, if one submodule contains another submodule, then the same inclusion you have in image. That is isomorphism theorem. So there is a one-to-one correspondence between submodules of m containing m and all submodules of m over n. That is a universal theorem. It holds for groups, it holds for rings, it holds for modules, it holds for algebras as well. So in algebras case also we can find similar things. Okay, so I had to stop here for the first part. Thank you.